Hi guys, welcome back. This is the last one for 5.2. We're looking at properties of definite integrals. We're not going to learn how to actually take it yet. We're just going to do the properties because if I showed you how to take it, you could just kind of skip over the properties and stuff. So I want you just to learn the properties here. So our first property is if a and b are the same number, like our integral is going over the same point and f is defined at that point, like it's not a vertical asymptote. So not vertical asymptote, but it actually has a value at that point, like f of a equals some number. Then the integral there, the area under the curve is 0 because the delta x would equal 0. So it doesn't matter what the height is, it'd be 0 times the height, which is going to be 0. So for instance, if we look over here, we're going from pi to pi of sine of x, that's just 0. I don't care how high up it is at pi or how low it is at pi, it's just going to be 0. All right, next property. If f of x is integral on the a to b, so if we can actually take the integral from a to b of f of x, and it's some number, whatever it is, if we switch the bounds, so we switch them, switch the order, then we end up with a negative sign out front. So it negates it, it switches the sign. So if we're integrating backwards, so like this would be like integrating forward, this would be like, okay, now our integrals are going backwards. It basically changes the sign of our delta x, and we bring that sign out front. Like, because this would be b minus a over n, and this would be a minus b over n. They're going to have different signs. Like, this is the same thing as negative b minus a over n. See how we get the extra negative sign? That's where this negative sign is coming from. All right, so for instance, if I look at this guy, the integral from 3 to 0, well, we could rewrite that as the negative integral from 0 to 3. Like that. All right, and usually that's how we do it. Usually a is the smaller number and b is the bigger number. Usually that's what we like to do, but sometimes there are reasons to turn it around. It's easier to do and things like that. All right, but that's what we want to see from that. And the last property here that we're looking at is if c is some number, doesn't even matter if it's between a and b. It could be outside of a and b or it could be between a and b. Between a and b kind of makes more sense when you think about it like area-wise. So like we've got some curve, here's a, here's b. I'm treating this as my x-axis, and like here's c. All we're saying is the area from a to b, the whole section, is the same thing as the area from a to c, which is this guy, plus the area from c to b, which is that guy. So, I mean, that makes perfect sense to me. If it's in between, yeah, you just break it up, and it's those two areas add up to the whole area, and that's all that's saying. If c is outside of it, it still works. All right, because one of those integrals will be going backwards, and one of those integrals will, like if we do it like this, so here's a, maybe here's b, and here's c. So a to c is going to go all the way to there, and then we'll be going from c to b. That'd be taking away this area because it'd be the bounds would be backwards. We'd have to turn the bounds around, and it would become negative, and it would cancel out this section here. All right, so the time when this is most often used is when we're working with absolute value or with a piecewise function. So we could break this up at 0. So this would be the integral from -1 to 0 of the absolute value of x dx plus the integral from 0 to 1 of the absolute value of x dx. And the reason why we like to do that is because the absolute value of x is generally defined as that piecewise function. It's negative x when x is less than 0, and it's just regular old x if x is greater than or equal to 0. So we could say that this is negative x in here, and this is just x in here, and we get rid of the absolute value. All right, so some other rules. So we mentioned this before with the summation. If we have a constant in here, the constant can come out front. It works for definite integrals, and it works for indefinite integrals. Think about it this way. So here's maybe our f of x. If we multiply it by a constant, like if k was 2, if we were just to double it, maybe it would move up to there, 2 f of x. All right, so we would just take this area from a to b, and we would have this plus this. It would just double. Right? So the k can just come out in front. I guess that's probably easier to see with just a rectangle, but you know, whatever, it works. All right. Now, if we're adding or subtracting two functions, and we're taking the integral of them, the definite integral, we're finding the area under the combination of them, we can separate it. And we can just say it's the integral of the first function plus or minus the integral of the second function. So the sign stays the same in between, and we just separate it into two separate integrals. All right. If f is integrable and non-negative on the interval, then the integral will be greater than or equal to 0. This one should be, here's f. Maybe I'll make it funky looking. And maybe here's b, here's a. So like this section here, sure, that would be 0, but we're still getting a positive area from that, and we're getting a positive area there. So our area is going to be greater than 0. Or it could be equal to 0 if we're going like from there to there, say. But our area will always be greater than or equal to 0 if our function is greater than or equal to 0. If our function's negative, our area is going to be negative. If our function's positive, our area is going to be positive. If our function's equal to 0, our area is going to be 0. All right. If f and g are integrable on the interval, and if f is always less than or equal to g, then the integral of f is less than or equal to the integral of g. Let's take a look. So maybe here's f. And let's switch to another color. Here's g. Maybe we'll make them equal to like this little section here. But then we'll make g bigger again. So if we want to look at, say, some interval here from a to b, sure, the integral of g should be bigger because it has all this extra area over here and all this extra area over here. So definitely the area under g will be bigger, so that means the integral for g will be bigger. All right? Always just think of these definite integrals as areas. Always think of them as areas. All right, so that's our properties of definite integrals. In 5.3, I think we'll go back and I'll actually show you how to take definite integrals, but now you've got to be able to do it with properties instead of actually just using the integral formulas.